You're running a packaging line, labeling bottles before they ship out. Most labels go on quickly, but every once in a while, a few take longer than expected. You want to demonstrate how that small variation at one step can have a much bigger impact on everything that happens afterwards, and why reducing variation matters so much. How do those small delays affect the rest of the line? Does variation in one step slow everything down? And when does it start to matter? There's a model for that. Welcome to Model Monday, a series where we break down scenarios in different industries, organizations, and departments, and explain how you can build a simulation of them in Process Playground. Let's model it. This model will feature two different manufacturing lines, each handling the same amount of demand. The first line will have higher variation, and the second line will have lower variation. The first thing we'll do is create our different item types. For this model, it's important that we provide the same amount of demand to both lines. We will do this by having a combined item and then splitting it to go down each line. First, we'll have line 1. These items will go down line 1. Then we'll create a second item we'll call line 2, and these will go down our second line. Then we're going to create an item type called combined items so that things will get split off equally. We'll add line 1 and line 2 to this item, and then when it reaches a split block, it will produce each of these two items. Next, we'll create demand. In this demand block, we're going to create these combined items. For the purposes of this demo, we're going to say it generates one item every minute. Next, we'll add the split block, and we have to add the combined items to this block, and this tells it what type of item it needs to be splitting. Now we're going to set the items to go down each of the lines. We're going to first add this queue, and we'll call it Q1, and we're going to turn off Allow All Items, and only add line 1 to this block. Now, only line 1 items will go down this path. Then, we'll add a second queue, and we will call this Q2, and we'll turn off Allow All Items, and we will add line 2 so that only line 2 items will go down this path. Now we'll create two different activity blocks on each line representing different levels of variation. So I'm going to click on this queue so that I can create an automatic line between our two blocks, and I'm going to call this activity block Labeling 1. Here's a quick tip. Since only line 1 items are already going down this path, we don't have to turn off Allow All Items in our future blocks. This activity block will represent our higher variation, so let's set it to a normal distribution with a mean of 1 and a standard deviation of 0.6. Then we'll do the same for the activity block for our second line, and we'll call this Labeling 2, and we'll set the distribution to a normal distribution. We'll keep the same mean for this line, 1, but we're going to have less variation, a mean of 1 and a standard deviation of 0.1. We can add additional notes to our simulation by using text blocks to provide further annotations to our model. In this case, we'll add the settings in text outside of the blocks as a reminder. So this first one has a mean of 1 with a standard deviation of 0.6, and our second block also has a mean of 1, but a standard deviation of 0.1. Now let's create an exit for each of these blocks. I will click on the activity and I will drag on the exit to give that automatic connection. And I'll rename this exit 1. And again, we don't have to click off Allow All Items in this case. We can come down here with line 2. I'll pull out an exit block. I'll change the name to exit 2 and we'll just leave on Allow All Items. Great. Now we've got two lines with the same amount of demand running through it, and the main difference is the amount of variation in the activity block. We're going to run this for 4,000 minutes, and we're going to make sure this is set to 1 run, and we'll run our model. Here are a couple of things that we want to look at. First, we can see here in line 2, which was less variable, that we got more output than we did in line 1. We also have a bit more sitting in the first queue before the activities in our first line compared to our second line. We can also look at our summary statistics. For our exit blocks, we'll double-click and go to Results, and we'll take a look at the total lead time, which is the average amount of time spent in the process before arriving at this block. Since this is our exit block, it is the average amount of time items spent in the entire process. and we're going to click on Apply to all exit blocks. We can see here the total lead time of 23.5 minutes versus 4.5 minutes. It's dramatically better for the one with less variation. Let's look at the activity block. What we probably care about most is our block cycle time. This is the amount of time the items spend in this particular block. So we'll click this on and we will apply it to all activity blocks. As we would expect, we put in a mean of 1 and we're getting approximately a mean of 1. We won't get exactly 1 all of the time because our models are non-deterministic. Then we can look at the cues, and the cues are really going to tell this story. So let's look at the count, the average length of the cue, the maximum number that ended up in this queue, and the block cycle time, the amount of time items spent in this block. And let's apply that to all blocks, so both of our cues. We can see that for the more variable line, the average length of this queue was definitely much higher than for the line that was less variable. In addition, we can see that the block cycle time for this top queue was 22.5 minutes versus 3.5 minutes. Another dramatic difference. Sometimes, when you're running a simulation, results can happen by chance and chance alone. So what we want to do is run this simulation multiple times, and there's an easy way to do that in Process Playground. We'll put 10 in the number of runs section, and this will run the simulation multiple times, and we'll get the statistics out in a format of mean and standard deviation across all 10 of these runs. Here's a quick tip. Generally speaking, we recommend not setting this number to more than 10. So let's go into our exit block and turn on our statistics. You can see here it's 70.26, but that only represents our first run. If I click on this toggle, it'll give me the cross-run statistics. So now we will get the average across all 10 of our runs as well as the standard deviation. While that first run was about 70 something, across all runs we have an average of about 35 items and a standard deviation of about 16. If we look down at our second line, we can see that we are now at about 4 minutes across all 10 of our runs with a standard deviation of around 2. Let's take a look at the Q max. Across all 10 simulations, we have about 71 items with a standard deviation of 26 in our higher variation line. Down at our second line, you can see that our max length was around 8 across all 10 of our runs with a standard deviation of around 4. The other key statistics to look at is our block cycle time. And you can see in our first line, we have about 34 minutes with a standard deviation about 16. While in our less variable line, we have a cycle time of about 3 minutes and a standard deviation of 2.2. That is a huge difference between the two lines. Overall, the lesson of this is that the less variable your process is, the faster things will go through. So in a nutshell, that's the impact of variation model. But the real value is in what you can experiment with. By introducing small differences in how long one step takes, you can demonstrate the often much bigger impact that variation has on everything that happens afterward, even when the average time stays the same. Whether that's labeling bottles on a packaging line, inspecting parts in manufacturing, verifying prescriptions in a pharmacy, or checking in passengers at an airport. From here, you can start to ask real design questions. How much variation can the system absorb before queues start to grow? Should I add capacity to absorb the variation? Should I add buffers between steps? Or should I focus on reducing the variation itself? Those are the kinds of operational trade-offs this model is built to explore. That's the model. Now go experiment. Happy modeling!